Right now, as you listen to these words, a metal object the size of a small car is flying through absolute emptiness at a speed of more than 60,000 kilometers per hour. It is so far from Earth that light, the fastest thing in the universe, takes almost 23 hours to reach it. This object left our planet 46 years ago, when your parents might not have even been born yet. And what it discovered there, in interstellar space, contradicts everything scientists assumed about the boundaries of our solar system. This is not science fiction. It is a reality we created with our own hands in 1977. And today, this reality sends us signals from a depth of space that the human mind can barely comprehend. On this journey, you will learn 3 secrets that will change your perception of our place in the universe. First, what actually lies beyond the solar system, and why it turned out to be something completely different from what astronomers expected. Second, what strange sound Voyager's instruments recorded as they crossed the invisible boundary between our home and the infinite darkness. And third, why what the spacecraft discovered may mean that we are much more alone in this universe than we ever thought. You will learn something that will keep you awake, or, conversely, plunge you into the deepest reflections as sleep slowly envelops your consciousness. If you are fascinated by the mysteries of space, subscribe to the channel. The journey begins right now. When we talk about the Voyager mission, most people imagine a simple success story. 2 spacecraft, launched a few weeks apart in 1977, set off to explore the outer planets of the solar system. They photographed Jupiter and its raging Great Red Spot, flew past Saturn's rings, discovered volcanoes on the moon Io, and geysers on Triton. It was a triumphant era of space discovery, the golden age of planetary science. The official version states that after completing their primary mission, the probes simply continued their journey into space, gradually moving away from the Sun until they crossed the boundary of the heliosphere and entered interstellar space. Voyager 1 did this in 2012, Voyager 2 in 2018. Scientists celebrated. Newspaper headlines screamed that humanity had finally left its cosmic home. This version is beautiful. It is inspiring, and it hides something much stranger, because when Voyager 1 approached the edge of the solar system, its instruments began to record data that did not fit into any existing model. Scientists expected a smooth transition. They expected the solar wind, the stream of charged particles that the sun ejects in all directions, to gradually weaken until it disappeared completely. Instead, the craft discovered a zone of chaos. Imagine it like this. You are floating down a calm river and see the ocean ahead. You expect the river to simply flow into the sea and mix with its waters. But instead, you find that between the river and the ocean, there exists a wall of churning foam, whirlpools, and unpredictable currents. That is exactly what Voyager found at the boundary of our solar bubble. The heliopause, as scientists call this boundary, turned out not to be a thin line, but a complex, multi-layered structure that behaves completely unpredictably. In some places, the solar wind suddenly intensifies, even though it should be weakening. In others, the interstellar medium seems to penetrate inside the heliosphere, creating pockets of alien matter within our solar home. Magnetic fields twist into spirals that do not obey any known laws. But this was only the beginning of the oddities. When Voyager 1 finally crossed the boundary and found itself in interstellar space, its plasma instrument recorded something inexplicable. The density of matter turned out to be higher than assumed. Not just a little higher, but significantly higher. The void between the stars turned out not to be as empty as astronomers had thought for decades. And that is not even the strangest part. The strangest part is the sound. You have probably heard that there is no sound in space. This is true in the sense we are used to. There is no air to transmit sound waves. But plasma, the ionized gas that fills the space between stars, can vibrate. And these vibrations can be converted into sound that the human ear can hear. When scientists did this with Voyager's data, they heard something that made them go silent for several minutes. A low, monotonous hum, constant, unchanging, endless. As if the universe itself is humming on one note. As if something out there in the infinite darkness between the stars is resonating. The official explanation states that this is simply a vibration in the density of the interstellar medium under the influence of distant cosmic events. But there is something unsettling about this sound. It is too stable, too constant, too much like something purposeful. But the reality turned out to be much darker than we could have imagined. You see, everything we knew about the boundary of the solar system was based on theoretical models, beautiful mathematical equations that worked perfectly on paper. Scientists were sure they understood how the heliosphere was structured, the protective bubble the sun creates around itself with its wind. They thought this bubble was shaped like a comet, round at the front and trailing a tail at the back in the direction opposite to the sun's movement through the galaxy. Voyager's data destroyed this model completely. It turned out that the heliosphere does not look like a comet. It does not look like anything we could have predicted. Recent studies based on data from both probes show that our solar bubble has a shape we are not even sure of. Perhaps it is a flattened disk, perhaps something like a croissant. Yes, that is exactly how scientists put it in one publication. Perhaps the structure is so complex and changeable that it is impossible to describe it with a simple geometric shape at all. This means that 40 years of space science were based on incorrect perceptions. It means that all our models of how the solar system interacts with the surrounding cosmos need to be revised. And it means that we have no idea what protection the heliosphere actually provides us from interstellar radiation, and this leads us to an even more disturbing discovery. Voyager found that the intensity of cosmic rays outside the heliosphere is much higher than inside it. This was expected. After all, that is exactly why the solar bubble exists, to protect us from galactic radiation. But the scale of the difference turned out to be terrifying. Cosmic rays are not rays in the usual sense. They are particles, protons, helium nuclei, sometimes heavier elements. They fly through the galaxy at speeds close to the speed of light. Some of them are products of supernova explosions. Others are ejections from black holes. When such a particle hits a living cell, it tears through the DNA, it causes mutations, it kills. The heliosphere is the only thing protecting Earth from this deadly stream. And Voyager showed us how thin this protection is, how unstable it is, how much it depends on the whims of solar activity, which changes in 11-year cycles. There are periods when the sun weakens, when the solar wind fades, when the heliosphere shrinks. In such periods, more cosmic rays penetrate inside our solar home. They reach Earth. They bombard our atmosphere. Most of them are absorbed by the air, but some reach the surface. We live under constant shelling without even knowing it. And only thanks to Voyager are we beginning to understand the true scale of the threat. But wait, the story gets even stranger. In 2020, Voyager 1 recorded something that scientists still cannot fully explain. A surge in electron density in the interstellar medium. Sharp, sudden, for no visible reason. As if something happened in the space between the stars. As if some wave passed through the void. Presumably, this was a shock wave from a distant solar flare from our own sun, which reached interstellar space several months later. But the calculations do not match perfectly. The time frames are slightly shifted, the intensity is slightly higher than expected. Some researchers suggest that the source could have been different, that the wave could have come from deeper space, that Voyager could have witnessed an event that occurred in another star system, the echoes of which rolled through the interstellar medium. We are in an ocean that we do not understand. We sent a bottle with a message, and it returned an echo of something vast and incomprehensible. Let us go back to the beginning of the mission to understand how we ended up at this point. 1977. an era when humanity still believed in the boundless possibilities of space expansion. It had been only 8 years since the first moon landing. It seemed that colonies on Mars were a matter of the next few decades, that by the end of the century, people would be living on orbital stations by the thousands. It was in this atmosphere of optimism that NASA developed one of the most ambitious missions in history. 1977 presented a unique opportunity. Once every 175 years, the giant planets align in space in such a way that a single spacecraft can sequentially visit all 4 of them. Using the gravity of each planet to accelerate toward the next, this opportunity could not be missed. The next such chance will not appear until the year 2100 and something, when none of us will be here. 2 probes, Voyager 1 and Voyager 2, were created for this journey. Paradoxically, Voyager 2 was launched first on August 20, 1977. Voyager 1 started 16 days later, but on a faster trajectory that allowed it to overtake its twin. Each probe carried an identical set of scientific instruments: cameras, spectrometers, magnetometers, particle detectors, and each carried something special: a golden record. Voyager's golden record is perhaps the most ambitious act of interstellar communication in human history. On it are recorded the sounds of our planet: whale song, children's laughter, music from different cultures, from Bach to tribal drums. On it are images of people, animals, landscapes. On it is a greeting in 55 languages. On it is a diagram of the sun's position relative to pulsars, a kind of cosmic map of our location. We sent a message in a bottle into an ocean the size of which we cannot even imagine. And here is the scary part. This bottle has been flying for 46 years. It has traveled almost 24 billion kilometers. It has gone beyond the sun's influence, and it has reached nothing yet. The nearest star, Proxima Centauri, is about 4 light-years away from us. That is 40 trillion kilometers. At its current speed, Voyager 1 would need about 70,000 years to cover that distance, and Proxima Centauri is not even on its path. The nearest star Voyager 1 will fly past is Gliese 445 in the constellation Camelopardalis. It will reach its vicinity in about 40,000 years. 40,000 years. The entire written history of humanity fits into 5,000 years. The entire history of Homo sapiens as a species into 300,000. Voyager will be flying to its first star longer than any human civilization has existed. And most disturbingly, we do not know if anyone will be there to receive its message. We do not know if anyone is out there in the dark. We do not know if we are alone. Voyager flies through a void that stretches for trillions of kilometers, and every day it sends us signals. Weak, barely detectable, with a power of only about 23 watts, less than a light bulb in a refrigerator. These signals travel a distance of 23 light hours, scattering in space, weakening to unimaginably small values, and we hear them. Giant antennas of the Deep Space Network in California, Spain, and Australia are pointed at the point in the sky where Voyager is located. They catch its whisper from the abyss. They record the data it continues to collect, but time is running out. Voyager's radioisotope thermoelectric generators, its only power source, are slowly dying. The plutonium-238 they contain decays with a half-life of 87.7 years. Every year, the probe loses about 4 watts of power. Scientists have already begun to turn off scientific instruments one by one to save energy for the most important thing: communication. By 2030, perhaps earlier, no energy will be left even for the transmitter. Voyager will go silent. It will continue its flight through interstellar space, but now as a silent messenger, like a dead ship in an infinite ocean, and we will never know what else it could have told us about what lies further ahead. This is a strange thought to hold in your mind. Right now, at this second, we are connected by a thin thread of radio waves to an object that is further from Earth than any other creation of human hands, and this thread will soon break. But what Voyager has already managed to tell us has changed our understanding of the universe forever. The data it continues to transmit is full of mysteries that we are only beginning to solve. And some of these mysteries point to a reality so strange, so contrary to our expectations, that scientists are still debating their interpretation. In the next part, we will dive into the scientific details of exactly what Voyager discovered at the edge of the solar system and beyond. We will talk about the heliopause, this strange, flowing boundary between our cosmos and the alien one. We will learn about how the solar wind collides with the interstellar medium, creating a zone of turbulence that stretches for billions of kilometers. And we will begin to understand how fragile that bubble is, within which our world exists. For now, just allow yourself to realize the scale of what we are talking about. A spacecraft the size of a small car, launched in an era when computers occupied entire rooms, working on technologies that were outdated before you were even born, flying through the void faster than a bullet and transmitting to us a voice from the abyss. To truly understand what Voyager discovered, we first need to understand what it has been flying through all these decades. We need to understand what the heliosphere is, not as an abstract concept from a textbook, but as a real physical structure that you are inside right now. Imagine the sun not as a bright disk in the sky, but as what it actually is, a giant thermonuclear reactor almost 1.5 million kilometers in diameter. Every second, 600 million tons of hydrogen are converted into helium in its core. This process releases energy equivalent to the explosion of hundreds of billions of atomic bombs every second without stopping. For 5 billion years, part of this energy has reached us in the form of light. But there is another flow, the solar wind. This is not wind in the usual sense. It is a stream of charged particles, mainly protons and electrons, that the sun continuously ejects in all directions. They burst out of the solar corona, the star's outer atmosphere where temperatures reach millions of degrees, and rush into space at speeds of 300 to 800 kilometers per second. Think about that number, 800 kilometers per second. In 1 second, a solar wind particle travels the distance from Moscow to Nizhny Novgorod. In a minute, it is already somewhere past the moon. In a few hours, it reaches Earth's orbit. In a few days, it gets to Jupiter. And this flow never stops. The sun loses about 1.5 million tons of matter every second. It sounds like a lot, but for a star, it is nothing. The sun can continue in this mode for billions more years. The solar wind carries the sun's magnetic field with it. It is frozen into the moving plasma like a thread in a cloth and stretches along with it for billions of kilometers. This creates the structure that scientists call the interplanetary magnetic field. It twists into a spiral due to the sun's rotation, the so-called Parker spiral, and permeates the entire space of the solar system. But the solar wind cannot fly forever. Sooner or later, it meets obstacles, the interstellar medium. The space between stars is not an absolute void. There is gas there, mostly hydrogen and helium. And this gas has its own pressure. It also carries a magnetic field, the field of the galaxy itself. And when the solar wind encounters this resistance, it begins to slow down. The first boundary the solar wind crosses during this deceleration is called the termination shock. Here, the supersonic flow of the solar wind suddenly becomes subsonic. Imagine a jet plane breaking the sound barrier. Only in reverse, the stream of particles slows down sharply, heats up, and becomes turbulent. Voyager 1 crossed this boundary in December 2004 at a distance of about 14 billion kilometers from the Sun. Voyager 2 did so in August 2007 at a slightly smaller distance, about 13 billion kilometers. Even this difference was surprising. The boundary turned out to be asymmetrical. It pulses and breathes depending on solar activity. No, the termination shock is not yet the exit from the solar system. Beyond it lies a region called the heliosheath. This is a zone of turbulence where the slowed solar wind mixes with particles from the interstellar medium. Chaos reigns here. Magnetic fields intertwine, particle streams change direction, and temperature and pressure jump unpredictably. Voyager spent years in this zone, and what it discovered there forced scientists to reconsider their ideas about cosmic plasma physics. One of the most unexpected discoveries was the so-called magnetic foam in 2011. Data from Voyager 1 showed that in the heliosheath, the magnetic field is not smooth and uniform as expected. Instead, it is broken into trillions of tiny bubbles, each about 160 million kilometers in diameter. That is roughly the distance from Earth to the Sun. These magnetic bubbles form due to instabilities in the solar wind flow. Magnetic field lines intertwine and break, creating closed structures. The craft flies through this foam, crossing the boundaries of the bubbles about once a day. Each time, magnetometers record a sharp change in the field direction. This discovery had important consequences. Magnetic foam, as it turned out, affects how cosmic rays penetrate the solar system. Previously, scientists believed that charged particles from deep space simply slid along the lines of the interplanetary magnetic field like on rails. But magnetic foam is not rails. It is a labyrinth. Particles get tangled in the intertwinings, get stuck in bubbles, and slowly diffuse through the chaotic structure. On the one hand, this is good. The foam provides additional protection from galactic radiation. On the other hand, it means that our models of cosmic ray propagation were inaccurate, and that means our predictions of the radiation environment in interplanetary space, the very predictions we rely on when planning manned missions, could contain serious errors. But magnetic foam is only one of the oddities discovered in the heliosheath. Another concerns the direction of particle movement itself. Inside the solar system, the solar wind blows radially, straight from the sun in all directions. This is logical, expected, and confirmed by decades of observations. But in the heliosheath, everything changes. The slowed wind can no longer move radially. It has nowhere to go. It begins to flow sideways toward the flanks of the heliosphere. Voyager 2 recorded that in the heliosheath, the speed of radial plasma movement dropped almost to zero. Particles were no longer flying away from the sun. They were moving predominantly in a transverse direction. This confirmed theoretical predictions, but the scale of the effect exceeded expectations, and then there were the temperature anomalies. When the solar wind crosses the termination shock and enters the heliosheath, it should heat up. The kinetic energy of the directed motion transitions into the thermal energy of the chaotic movement of particles. Calculations predicted that the plasma temperature should jump to millions of degrees. Voyager found that this was not the case. The temperature turned out to be significantly lower than predicted, only a few 100,000 degrees. Where did the missing energy go? Scientists are still debating the answer. One hypothesis states that part of the energy went into accelerating a small population of particles to very high speeds, the so-called anomalous cosmic rays. Another is that the energy dissipated in the form of plasma waves that Voyager's instruments were not capable of recording directly. A third is that our models of shock waves in cosmic plasma are fundamentally incomplete. The truth is most likely somewhere between these options, but it shows how complex reality turned out to be compared to our theories. Let us talk about Voyager's instruments, because they are the key to understanding how we even get this information. Each probe carries 11 scientific instruments, or rather, it carried them. Many of them have already been turned off to save energy, but at different times they all worked, collecting data about space. The plasma spectrometer measures the properties of the solar wind, particle speed, density, and temperature. It was this instrument that recorded the dramatic drop in wind speed in the heliosheath. It was the one that confirmed the crossing of the heliopause when the solar wind disappeared completely. The magnetometer determines the direction and strength of the magnetic field. It is located on a long boom, 13 meters from the main body of the probe, to avoid the influence of Voyager's own magnetic fields. Magnetometer data allowed the discovery of magnetic foam and recorded the sharp change in field direction upon crossing the heliopause. Low and high-energy particle detectors register cosmic rays, from relatively slow particles to ultra-relativistic nuclei flying at nearly the speed of light. They showed how the intensity of galactic radiation grows with distance from the Sun and recorded that very jump upon entering interstellar space. The plasma wave instrument is perhaps the most poetic tool. It measures electrical vibrations in the plasma and allows us to hear space. It was this instrument that recorded that low hum of the interstellar medium, which scientists converted into sound for the human ear. The ultraviolet spectrometer studies the glow of gas in space. It discovered a faint ultraviolet glow beyond the heliosphere, the so-called hydrogen wall, where interstellar gas is compressed in front of the heliosphere like water in front of a ship's bow. Each instrument is a window into an invisible world. We cannot see magnetic fields with our eyes, we cannot feel cosmic rays with our skin, we cannot hear plasma waves with our ears. No, Voyager's instruments translate all these phenomena into a language we can understand, the language of numbers, graphs, and signals. And here is what is amazing. These instruments were developed more than 50 years ago. They are built on technologies from an era when personal computers did not even exist. The computing power of Voyager's onboard computer is about 69 kilobytes. That is less than in a simple modern calculator. That is less than a single photograph on your phone takes up. And yet this ancient probe continues to make discoveries that outpace our most modern theories. Now let us move on to the most important part, the moment Voyager truly left the solar system. On August 25, 2012, something unprecedented happened. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, and entered interstellar space. For the first time in human history, a man-made object was outside the influence of our star. But the moment of crossing was not obvious. Scientists expected things to be simple. The solar wind would disappear, cosmic rays would increase sharply, and the magnetic field would change direction. 3 clear signs, 3 switches from the inside position to the outside position. Reality turned out to be more tangled. Cosmic rays did start to grow, the solar wind did disappear. But the magnetic field behaved strangely. Its direction did not change as expected. Instead of a sharp turn, there was a series of oscillations that lasted for months. This sparked heated debates in the scientific community. Some researchers claimed Voyager had already entered interstellar space. Others argued it was still in some kind of transition zone, an unknown region at the edge of the heliosphere. Third ones suggested that our ideas about the interstellar magnetic field were wrong from the start. The disputes lasted for over a year. In the end, the decisive evidence came from the plasma wave instrument. In April 2013, it recorded oscillations in electron density caused by a solar flare that had reached the spacecraft's location. The frequency of these oscillations allowed the calculation of the surrounding plasma density, and it turned out to be about 40 times higher than in the heliosheath. This was the density of the interstellar medium. Voyager had indeed gone outside, but the mystery of the magnetic field remained. Theorists predicted that the interstellar magnetic field should be oriented completely differently from the solar one. But Voyager's data showed that the direction had hardly changed. The field lines were still oriented roughly the same as they were inside the heliosphere. How is this possible? One explanation is that the heliosphere deforms the surrounding interstellar magnetic field so strongly that it flows around it, aligning itself with the orientation of the solar field. Like a river flowing around a stone takes the shape of its contours. But this requires very specific conditions and coincidences. Another explanation is that we still do not understand exactly where Voyager is. Perhaps it crossed the heliopause, but did not fully leave the sun's zone of influence. Perhaps there is another boundary further out that we have not yet reached. Some scientists suggest the existence of a so-called hydrogen wall, a region where interstellar hydrogen accumulates in front of the heliosphere, compressing and heating up. This region could stretch for billions of kilometers beyond the heliopause, creating a kind of buffer zone between solar influence and true interstellar space. The truth is, we do not know for sure. We have only one spacecraft in this region of space, and its capabilities are limited. Instruments designed to study planets are not perfectly suited for exploring the interstellar medium. Many questions will remain unanswered until we send a new mission there with modern instruments and a broader set of sensors. But such a mission is a matter of decades. Even if we launch it tomorrow, it will take years before it reaches the boundaries of the heliosphere. And Voyager is dying. That is a strange word for a machine, but it accurately reflects what is happening. The plutonium in its generators is decaying, power is dropping, instruments are being turned off one by one, and the heaters that protect the devices from cosmic cold no longer work. Fuel for the orientation thrusters is running out. In 2022, engineers discovered a strange problem. Voyager 1's telemetry system began transmitting nonsensical data about the craft's position. The antenna was still pointed at Earth, but the onboard computer reported it was pointing in a completely different direction. For several months, the mission team searched for the cause and a solution. They found it. It turned out that one of the probe's outdated computers had failed, and the system began sending data through a non-functioning module. Engineers, many of whom have long been retired, returned to decipher code written half a century ago. They found a workaround. They saved the mission, but this is a temporary measure. Each year brings new problems. Each year, less safety margin remains. By 2025, perhaps only enough energy for one or two instruments will be left. By 2030, perhaps only for the transmitter. And then, silence. And in that silence, Voyager will continue its journey. Without electricity, without heat, without communication with home, a dead ship in an ocean of darkness. But as long as it is alive, it continues to transmit data. And this data raises questions to which science has no answers. Why did the density of the interstellar medium turn out to be higher than predicted? Where do the strange oscillations recorded by the plasma wave instrument come from? Why does the magnetic field not behave as expected? What lies even further beyond what Voyager can measure? We sent a messenger into the unknown, and it returned more questions than answers. This is perhaps the best result science could have hoped for, because it is questions that drive knowledge, mysteries that force us to build new theories, develop new instruments, and send new missions. Voyager showed us that the boundary of the solar system is not a line on a map. It is a complex, dynamic, living structure. It breathes in the rhythm of solar activity. It oscillates under the pressure of the interstellar wind. It protects us from the deadly radiation of the galaxy. But this protection is not absolute. And beyond this boundary lies a space we are only beginning to learn about. The interstellar medium, the ocean between the stars, holds the history of our galaxy. Every atom there is a witness to stellar births and deaths, supernova explosions, and neutron star collisions. This medium carries the imprint of all events that have occurred in the Milky Way over billions of years. Voyager is our first direct contact with this ocean, the first sip of water from a source whose existence we only guessed at. And this sip turned out to taste strange. Not as we expected, not as our theories predicted. No, that is exactly why Voyager is so important. It teaches us humility. It reminds us that the universe is not obliged to meet our expectations, that reality is always more complex than models, that every answer gives birth to 10 new questions, and that the void between stars is not so empty. Now that we understand the structure Voyager has been pushing through, let us focus on specific events, moments when the probe witnessed something so unusual that scientists are still scratching their heads over the interpretation of the data. On November 5, 2012, about 2 months after crossing the heliopause, Voyager 1's detectors recorded a strange surge. The intensity of low-energy cosmic rays suddenly jumped by nearly 10% in a few hours. Then it just as sharply returned to normal. No visible source, no warning. As if an invisible wave rolled through the space where the craft was located. Scientists called this event a cosmic ray surge. The initial hypothesis linked it to a shock wave from a solar flare that caught up with Voyager several months after it occurred on the Sun. But the timing calculations did not match perfectly. The wave's propagation speed would have had to be higher to match the observations. An alternative explanation is even more intriguing. Perhaps Voyager crossed a local inhomogeneity in the interstellar medium, a pocket of increased matter density, a ripple in the ocean between stars left by some long-ago event. No, what event? Where did this ripple come from? The answer leads us into the past of our galactic environment, and that past turns out to be much more turbulent than one might expect. The solar system does not hang motionless in the void. It moves through the galaxy at a speed of about 220 kilometers per second, completing a full orbit around the galactic center in about 250 million years. And on its path, it passes through various regions of interstellar space, regions with different densities, temperatures, and compositions. Right now, we are inside a structure that astronomers call the local interstellar cloud. This is a relatively dense cluster of gas and dust, about 30 light-years in diameter. The Sun entered this cloud about 100,000 years ago and will leave it in 10 to 20,000 years. But the local cloud is just a small patch inside a much vaster structure. It is located at the edge of the so-called local bubble, a giant cavity in the interstellar medium about 300 light-years in diameter. Inside this bubble, the gas density is 10 to 100 times lower than in normal interstellar space. It is nearly empty here. It is hot. The gas temperature reaches 1,000,000 degrees. Where did this bubble come from? The answer is simple and terrifying at the same time. Supernova explosions. Over the last 10 to 20 million years, 15 to 20 massive stars have exploded in the vicinity of the Sun. Each explosion released energy into space equivalent to the Sun's total radiation over 10 billion years, its entire lifetime from birth to death. These explosions burned away the surrounding gas, pushed it aside, and created an expanding cavity. We live inside a scar from ancient cosmic catastrophes. Voyager is now flying through this scorched void. The data it transmits about the density and composition of the interstellar medium is a direct measurement of the consequences of those long-ago explosions. Every atom its detectors record is either a fragment of an exploded star or a witness to its death. And this explains some of the mysteries the mission encountered. Remember how Voyager found that the density of the interstellar medium was higher than expected? This might have seemed strange, since we are inside the local bubble where the density should be below average. No, Voyager is moving toward the edge of this bubble, toward the region where it borders the local interstellar cloud. There, the density is indeed higher. There, matter ejected by supernovae has accumulated in a kind of wall around the cavity. The craft is flying toward the wall, a boundary between void and matter. And this boundary is a trace of violence that occurred millions of years ago. But let us talk about more recent events, the ones Voyager recorded directly. In 2014, the plasma wave instrument detected a repeating signal, not a single surge, but a series of oscillations that lasted for several months. The frequency of these oscillations changed slowly, as if someone were tuning an invisible instrument. Scientists determined the source. It was echoes of solar flares. When a massive coronal mass ejection occurs on the Sun, billions of tons of plasma flying into space at speeds of thousands of kilometers per second, this flow spreads through the entire solar system. It reaches the boundary of the heliosphere in a few months. There, it collides with the interstellar medium, creating a shock wave. This wave continues its movement already in interstellar space. It compresses the gas in front of it, causes density oscillations, and generates electrical disturbances. And Voyager, already outside the heliosphere, records these disturbances. This means something amazing. We can hear the sun even from interstellar space. Our star continues to influence the environment far beyond its protective bubble. Its flares create ripples that carry across billions of kilometers. No, this influence is mutual. The interstellar medium also affects the heliosphere, and this influence could be much more significant than we thought. In 2020, Voyager 1 recorded something new: a constant hum, steady plasma oscillations that were not linked to any specific solar events. This hum lasted for months. Its frequency indicated the density of the surrounding environment, and this density remained remarkably stable. But then, in 2021, a sharp jump occurred. The density suddenly grew by about 15% for no visible reason, with no link to solar activity. What was it? One hypothesis: Voyager crossed the boundary between two different regions of interstellar space, entering a denser pocket of gas. Now, where did this pocket come from? Why are its boundaries so sharp? Another hypothesis, more unsettling: perhaps it was an external disturbance, a pressure wave coming from the depths of interstellar space, a trace of an event that happened somewhere in the galaxy, perhaps very far away, perhaps very long ago. The cosmos is not a static picture. It is an ocean full of currents, waves, and storms. Voyager is our first direct sensor of these cosmic currents, and what it discovers shows how dynamic and unpredictable the space between stars is. Now let us move on to what all this means in terms of the energy and violence hidden behind these seemingly quiet data. The cosmic rays Voyager records are not abstract particles. They are projectiles. Every proton of galactic cosmic radiation carries energy that might seem small on the scale of human experience, usually from 1 million to 1 billion electron volts. But on the scale of atoms and molecules, this is a colossal energy. When such a proton hits a living cell, it pierces right through it, like a bullet through a sheet of paper. On its path, it ionizes atoms, breaks molecular bonds, and damages the DNA. A single particle can cause a mutation. Thousands of particles accumulated during a spaceflight can cause cancer. Outside the heliosphere, the intensity of this radiation is about 3 times higher than inside. Voyager measured this difference directly, and this difference is a measure of how much the heliosphere protects us from galactic violence. No, protection is not absolute. Part of the cosmic rays penetrate inside. They bombard Earth constantly, about 10,000 particles per square meter per second. The atmosphere absorbs most of them, creating cascades of secondary particles that are mostly harmless by the time they reach the surface. But not all of them. Cosmonauts on the International Space Station receive a radiation dose about 200 to 300 times higher than people on Earth. This is still tolerable for short missions. But for a flight to Mars, which will take months in one direction, the accumulated dose becomes a serious problem. And now imagine a flight to the stars. Years and decades, centuries in interstellar space where there is no protection, where the intensity of cosmic rays is many times higher, where every second your body is pierced by particles carrying the energy of nuclear reactions. Voyager showed us what future interstellar travelers will face. And the picture is not encouraging, but cosmic rays are just the tip of the iceberg. Let us talk about where they come from, because it is a story of galactic-scale violence. Most cosmic rays are born in the shock waves of supernovae. When a massive star explodes, it ejects its shell at a speed of tens of thousands of kilometers per second. This shell slams into the surrounding gas, creating a shock wave. In this wave, particles are accelerated to relativistic speeds close to the speed of light. The mechanism is called diffusive shock acceleration. Imagine a particle bouncing between two converging walls, like a ball in a narrowing corridor. Each bounce adds energy to it. On a cosmic scale, the walls are magnetic inhomogeneities on both sides of the shock wave. The particle crosses the wave front again and again, gaining speed each time. This process continues for thousands of years while the supernova remnant expands and cools. During this time, some particles manage to gain energy in the millions and billions of electron volts. Then they break out of the remnant and fly into interstellar space. They fly through the galaxy, deflected by magnetic fields and scattered by inhomogeneities. Some reach our solar system, some Voyager, some Earth. Every cosmic ray Voyager records is a messenger of a distant catastrophe, a fragment of an exploded star flying through the universe at a speed close to the absolute limit. But supernovae are not the only source. The most energetic cosmic rays, those whose energy exceeds trillions of electron volts, are likely born in even more extreme conditions. In the jets of active galactic nuclei, where supermassive black holes eject matter at speeds close to light, in collisions of neutron stars generating gravitational waves and particle streams, in gamma-ray bursts, the most powerful explosions in the universe. There are particles with energy that defies comprehension, so-called ultra-high-energy cosmic rays with energy over 10 to the 20th power electron volts. One such particle, a single proton, carries energy comparable to the energy of a tennis ball flying at 100 kilometers per hour. All this macroscopic energy is concentrated in a single subatomic particle. Where such monsters come from, we do not know exactly. No known mechanism can fully explain their acceleration. This is one of the great mysteries of modern astrophysics. And Voyager, though its detectors are too weak to register such extreme particles, is flying through a space filled with these messengers of violence. It is swimming in an ocean of energy that might seem invisible but is capable of killing any living being without protection. Now let us talk about another source of cosmic violence that directly affects the heliosphere and everything inside it: galactic magnetic storms. We are used to solar magnetic storms. When the sun ejects a coronal mass in our direction, charged particles collide with Earth's magnetosphere, causing geomagnetic disturbances, auroras, interference in radio communications, sometimes power grid outages. This is a familiar threat we have learned to track and prepare for. But there is a larger-scale threat. The interstellar medium is inhomogeneous. It contains clouds of different densities, gas flows with different speeds, and magnetic structures of different orientations. As the solar system moves through the galaxy, it inevitably collides with these inhomogeneities. Currently, we are in a relatively calm region inside the local bubble at the edge of the local cloud. But it was not always this way, and it will not be this way forever. Geological and paleontological data show that in the past, Earth experienced periods of increased cosmic radiation. About 2.5 million years ago, around the same time our ancestors began using stone tools, the intensity of cosmic rays on Earth rose sharply. Traces of this event are preserved in iron-60 deposits on the ocean floor. Iron-60 is a radioactive isotope that is not produced on Earth. It can only come from space with supernovae or cosmic rays. What happened 2.5 million years ago? Perhaps a nearby supernova within a few hundred light years. Perhaps the solar system entered a denser region of the interstellar medium. Perhaps the heliosphere temporarily shrank, letting in more galactic radiation. We do not know for sure, but we know it can happen again. Voyager gives us the first direct measurements of what lies beyond our protective bubble. It shows us what kind of environment we will have to face when conditions change. It is a scout sent to the front line, and its data says the boundary is unstable. The heliosphere breathes in the rhythm of solar cycles. It expands when the sun is active and shrinks when activity drops. During solar minima, such as the recent minimum of 2019 to 2020, the boundary shifts inward by hundreds of millions of kilometers. This means the number of cosmic rays reaching the inner regions of the solar system fluctuates. In periods of minimum solar activity, Earth receives more galactic radiation. Not catastrophically more, the atmosphere still protects us, but enough to affect the climate and chemistry of the upper atmosphere. Some researchers suggest a link between solar activity, cosmic rays, and cloud formation in Earth's atmosphere. The theory remains controversial, but if it is true, then the oscillations of the heliosphere, the very oscillations Voyager tracks, could influence our planet's climate. We are used to thinking of space as something distant and unimportant for daily life. Voyager reminds us that this is not so. We live inside a star, inside its sphere of influence, inside its protective field. And everything that happens at the boundary of this sphere ultimately affects us. Now it is time to make the transition to the most extreme aspects of what is hidden in the interstellar darkness, to phenomena so powerful they can sterilize planets and cut short the evolution of life. Because Voyager is not just flying through a void, it is flying through a battlefield where forces of galactic scale clash in battles that last millions of years, and the traces of these battles are everywhere around it. The next part will tell about what happens when a supernova explodes nearby, about how gamma-ray bursts can destroy a planet's ozone layer in seconds, about why the silence of interstellar space is the silence of a graveyard, and about what conclusions we can draw from Voyager's loneliness in the abyss. Because the most terrifying thing the craft discovered in 46 years of flight is not strange data or unexpected instrument readings. It is silence, absolute, infinite, the silence of space. Imagine a star dying 50 light-years from Earth. That is not so far in cosmic terms. The nearest stars to us are at a distance of 4 to 5 light-years, and within a 50 light-year radius, there are about 1,500 star systems. One of these stars, massive, bright, unstable, exhausts its thermonuclear fuel and collapses. In fractions of a second, the star's core compresses to the size of a city. The density of matter exceeds the density of an atomic nucleus. The gravitational collapse releases energy equivalent to the sun's total radiation over 10 billion years. Most of this energy escapes as neutrinos, ghost particles that pierce through everything on their path, hardly interacting with matter. But a part, about 1%, turns into light, a shock wave, and particle streams. The supernova flares brighter than the entire galaxy. For several weeks it becomes visible even during the day. Ancient astronomers would have recorded it as a guest, a new star appearing out of nowhere. And then, the consequences begin. First comes the light, 50 years after the explosion. It is blindingly bright, but on its own, it is not dangerous at such a distance. Then the ultraviolet and X-ray radiation. They reach Earth almost simultaneously with the light and begin to destroy the ozone layer. In a few months of intense irradiation, the ozone content in the stratosphere drops by tens of percent. The sun's ultraviolet, which was previously absorbed by ozone, begins to penetrate to the planet's surface. Plants get burned. Phytoplankton in the upper layers of the ocean die. Food chains begin to crumble. Then, after several hundred or thousands of years, the cosmic rays arrive. The supernova shock wave accelerates particles to relativistic speeds, and they fly toward us through interstellar space. The heliosphere is not capable of fully stopping this stream. It only weakens it. The intensity of cosmic radiation on Earth increases many times over. Mutations in living organisms become more frequent. Cancer becomes an epidemic. This is not fantasy. This is a scenario that has likely already occurred in Earth's history. About 450 million years ago, at the end of the Ordovician period, one of the largest mass extinctions in the history of life occurred. About 85% of all marine species died out. Trilobites, brachiopods, bryozoans, entire groups of organisms were almost completely wiped out. The traditional explanation links this extinction to glaciation and a drop in sea level. No, some researchers suggest another cause, a gamma-ray burst. Gamma-ray bursts are the most powerful explosions in the universe. They occur when a massive star collapses into a black hole or when two neutron stars collide. In a few seconds, as much energy is released as the sun will emit over its entire existence. Most of this energy is concentrated in narrow beams of gamma radiation directed along the rotation axis of the collapsing object. If Earth finds itself in the path of such a beam, even at a distance of thousands of light years, the consequences will be catastrophic. Gamma rays will tear apart nitrogen and oxygen molecules in the upper atmosphere. Nitrogen oxides will form, which will destroy the ozone layer in seconds. Not in months, as with a supernova, in seconds. The planet will lose its protection from ultraviolet almost instantly. Models show that a gamma ray burst at a distance of about 6,000 light-years is capable of destroying half of Earth's ozone layer. Recovery will take years. During this time, the planet's surface will be irradiated with lethal doses of ultraviolet. The Ordovician extinction occurred about 445 million years ago. Traces of its causes have long since faded. We cannot know for sure if it was a gamma-ray burst, but statistics say that during the existence of life on Earth, about 4 billion years, such events must have happened repeatedly. We survived. Life continued, but that is no guarantee for the future. Voyager is flying through space where such events occur. Not near it, luckily, but somewhere in the galaxy. Every year, about 1 to 3 supernovae explode in the Milky Way. Every few million years, one happens close enough to affect Earth. Every few 100 million years, one is close enough to cause a mass extinction. It is cosmic roulette, and we are the ball rolling on its wheel. Now let us talk about specific threats, about stars we know by name that could explode in the foreseeable future. Betelgeuse, a red supergiant in the constellation Orion. Distance, about 700 light-years. Diameter, almost 1.5 billion kilometers. If Betelgeuse were placed in the Sun's position, its surface would swallow the orbits of Mercury, Venus, Earth, and Mars and reach the asteroid belt. Betelgeuse is dying. It has exhausted the hydrogen in its core and is burning helium. When the helium runs out, it will move on to heavier elements: carbon, oxygen, silicon. This process will take only a few thousand years. Then the core will collapse and the star will explode. When exactly, we do not know. Astronomy cannot predict supernova with millennial accuracy. It could happen tomorrow. It could happen in 100,000 years. But on the scale of the cosmos, that is a moment. In 2019, Betelgeuse suddenly dimmed. Its brightness fell by almost half. Astronomers around the world pointed telescopes at the dying star, wondering if this was the beginning of the end, if the core was collapsing right now. It turned out, no. The dimming was caused by a dust cloud the star had ejected in the preceding months. The dust blocked part of the light. Betelgeuse is still alive. But this episode reminded us how unpredictable dying stars are. When Betelgeuse explodes, it will be brighter than a full moon. It will be visible during the day for several weeks. Then it will fade, leaving behind a neutron star or a black hole. At a distance of 700 light-years, the explosion does not pose a direct threat to Earth. The dose of cosmic rays will increase, but not critically. The ozone layer will suffer, but not catastrophically. We will survive, but there are stars closer. Eta Carinae, a binary system at a distance of about 150 light-years. One of the components is a white dwarf, the dead core of a former star. It is slowly pulling matter from its companion. When the white dwarf's mass exceeds the critical limit, the Chandrasekhar limit, about 1.5 solar masses, it will explode as a Type 1a supernova. This will happen in millions of years when the stars get close enough for intense mass transfer. We will have time to prepare if we still exist as a civilization by then. Now, what about threats we do not know about? That is the horror of space. We see only part of the picture. Stars hidden by gas and dust clouds can explode without warning. Gamma-ray bursts come from galaxies billions of light-years away. and we only learn about them when the deadly beam has already flown past or through us. Voyager is flying through space filled with these hidden threats. Its detectors record particles, traces of distant catastrophes, but it cannot warn us of what is approaching. It can only tell of what has already happened. And here we come to the deepest question the Voyager mission poses. Why is it so quiet? 46 years of flight, 24 billion kilometers from Earth. Detectors capable of catching the weakest signals. Nothing. Not a single sign of other intelligence. Not a single hint that anyone else is sending probes into space. Of course, Voyager was not designed to search for extraterrestrial civilizations. Its instruments are tuned to study plasma, magnetic fields, and cosmic rays. But if other probes were flying in interstellar space, probes from other civilizations, one might expect at least some traces of their presence. Radio emissions from engines, thermal signatures, disturbances in the surrounding plasma. Nothing. The universe is silent. This silence has a name: the Fermi paradox. Formulated back in 1950, it asks a simple question. If the universe is so old and so large, if there are billions of potentially habitable planets in it, where is everyone? Where are the radio signals of other civilizations? Where are the probes similar to Voyager but launched millions of years ago by intelligent beings from other worlds? Where are the megastructures, Dyson spheres, or orbital settlements that should be visible to our telescopes? Silence. Voyager is our first step into interstellar space, and the first thing we discovered there is void. There are many explanations for the Fermi paradox, optimistic ones. Maybe civilizations are too far apart to meet. Maybe they use technologies we do not know how to detect. Maybe they are intentionally hiding. But there are also pessimistic explanations. They are linked to the concept of the Great Filter. The Great Filter is a hypothetical barrier that prevents the development of life to the interstellar level. It could be the emergence of life as such, a rarest event that only happened on Earth. It could be the transition from simple organisms to complex ones, the billions of years it took bacteria to become multicellular. It could be the development of intelligence, which appeared on Earth only once in 4 billion years. Or the Great Filter could be ahead of us. Maybe every civilization reaching a technological level destroys itself through nuclear war, ecological catastrophe, artificial intelligence gone out of control, or pandemics of laboratory-created pathogens. Or, and here we return to what Voyager showed us, maybe space itself is the filter. Remember what our little craft is flying through. Through space scorched by supernovae, through streams of lethal radiation, through an environment where a random gamma-ray burst can sterilize a planet in seconds, through a galaxy that kills without warning and without mercy. Maybe life arises often. Maybe intelligence develops everywhere. But maybe no one manages to reach the stars before the nearest supernova wipes them from the face of the universe. We might be the first to break through far enough. Or we might be the last of a long chain of failures. The silence of space is not proof of anything, but it is a warning. Now let us think about what all this means for us, for humanity, for our future, for our place in the universe. Voyager carried a golden record, a message to future finders. On it are recorded the sounds of Earth, images of people, a diagram of our location. It was an attempt to say, "We existed. We were here. We wanted you to know about us." But with every year of flight, it becomes clearer that this message may never be read. In 40,000 years, Voyager 1 will pass at a distance of about 1.5 light-years from the star Gliese 445. This is the closest approach to any star in the foreseeable future. 1.5 light-years, that is about 14 trillion kilometers. On the scale of star systems, this is a vast distance. The chances that someone will notice a tiny craft flying that far away are near zero. In 300,000 years, Voyager 1 will pass another star, TSC 3135, at a distance of a little less than a light-year. still too far. In millions of years, the craft will continue its lonely journey. It will drift through the galaxy, orbiting its center along with all the stars. It will survive the sun, which in 5 billion years will turn into a red giant and swallow the Earth. It will survive humanity, whatever our future may be. Voyager will become an artifact, an archaeological find on the scale of the cosmos, the most long-lasting creation of our civilization, and perhaps the only proof that we ever existed. This is a strange thought. In billions of years, when Earth is destroyed by the expanding sun, when all traces of our civilization have disappeared, Voyager will still be there. A small metal object flying through the void. Its electronics will have died long ago. Its golden record will have dimmed under the influence of cosmic rays, but the structure itself, aluminum, titanium, plastic, will be preserved almost forever in the cold and vacuum of interstellar space. If another civilization ever finds it in millions or billions of years, they will learn that there was life in this galaxy, that it developed to a level allowing objects to be sent to the stars, that it tried to speak to the universe. They will not know what happened to us. They will not know if we survived or perished. They will find only a bottle with a message floating in an infinite ocean. No, what is important to understand is that Voyager is not just a message in a bottle. It is a mirror. When we look at the data it transmits, we look at ourselves, at our place in the universe, at our fragility, at our uniqueness. Voyager showed us that the heliosphere, our protective bubble, is smaller and more unstable than we thought. That the space beyond its boundaries is more hostile than we assumed. That the space between stars is not a void, but an environment with its own laws and dangers. It showed us that we live on an island, a small, cozy island in the middle of an ocean of radiation and chaos. And this island is not eternal. The sun is aging. In 1 billion years, it will become bright enough to evaporate Earth's oceans. In 5 billion years, it will expand and swallow our planet. If humanity wants to survive in the long term, we will have to leave Earth, leave the solar system, and head for the stars. And Voyager is our first step on this path. Let it have been made without understanding all the consequences. Let the craft carry outdated technology and primitive instruments. Let it not even be able to slow down, doomed to fly straight forever. It is still the first step. We proved that we can send an object beyond solar influence. We proved that we can maintain communication across billions of kilometers. We proved that we can study interstellar space directly and not just theoretically. This is the foundation. Future missions will be built on it. Probes with nuclear engines capable of reaching the nearest stars in decades, not millennia. Telescopes using the sun as a gravitational lens to study exoplanets in detail. Maybe one day ships with people on board, but that is a matter for the distant future. Currently, we only have Voyager. Lonely, dying, moving away at a speed of 17 kilometers per second. Its voice is getting quieter. The energy in the generators is fading. Every year, the power drops by 4 watts. Instruments are turned off one by one. Soon, in a few years, only the transmitter will remain, and then it too will go silent. Voyager's last signal will travel over 20 light hours and reach the antennas on Earth. Weak, barely distinguishable, but still readable. And then, silence. We will wait for the next signal, but it will not come. We will send commands, but no one will answer. Communication with humanity's first interstellar messenger will break off, and Voyager will continue its journey in silence, a dead ship in a living universe, a monument to a civilization that dreamed of the stars. Right now, at this second, while you listen to these words, it is flying. Its antenna is still pointed at Earth. Its instruments are still collecting data. Its transmitter is still whispering to us from the abyss. This is not just a machine. It is a part of us, a continuation of our curiosity, our daring, our hope. We put into it all the best that 1970s humanity had: science, engineering, art, a dream, and it did not let us down. 46 years of continuous work, flybys of 4 giant planets, discoveries that rewrote textbooks, entry into interstellar space, data we will study for decades. A small craft weighing less than a ton did more for our understanding of the universe than a generation of philosophers debating space without leaving their offices. And here is perhaps Voyager's main lesson. The universe is vast, it is hostile, it is indifferent to our existence. No, we, small, fragile, living on a speck orbiting an ordinary star, we were able to send a messenger beyond its boundaries. We were able to look into the abyss and bring knowledge back from there. This is incredible. This is the most incredible thing any being we know of has ever done in the universe. Perhaps we are alone. Perhaps life is rare and intelligence unique. Perhaps in the entire galaxy there is no one who could appreciate what we have done. No, we did it anyway. Not for the sake of reward, not for the sake of recognition, for the sake of knowledge itself, for the sake of an answer to the question that has haunted our species since the first people lifted their eyes to the night sky. What is there beyond the horizon? Voyager is the answer. Not the final one, not the complete one, but an answer. There is space, there is plasma, magnetic fields, and cosmic rays. There are traces of exploded stars and the breath of the galaxy. There is an environment through which we will one day perhaps pave the path to other worlds, or not. Perhaps we will destroy ourselves before we learn to fly to the stars. Perhaps another supernova will decide our fate for us. Perhaps the universe is simply too big and we are too small. No, Voyager will fly. When the last human dies of old age, of catastrophe, of species extinction, Voyager will fly. When the sun expands and swallows the ashes of what was Earth, Voyager will fly. When the galaxy collides with Andromeda in 4 billion years, mixing stars in a cosmic waltz, Voyager will fly. It will fly until the universe itself dies, until the last stars go out, until the last black holes evaporate, until space itself stretches to infinity. And somewhere in that infinity, a small metal object with a golden record on board will drift. A message from a civilization that wanted to say, "We were here, we looked at the stars, we dreamed." Close your eyes. Imagine Voyager right now. A tiny point in the boundless darkness. The distant light of the sun, no brighter than an ordinary star somewhere behind. Around it, nothing. Only cold. Only vacuum, only the faint hum of plasma between stars. And inside that point is everything we wanted to say to the universe. The music of Bach and tribal drums, children's laughter and whale song, greetings in languages some of which are already dead, images of people who have long since passed away. This is us, frozen in metal and gold, flying forever. And if you listen closely enough, through the noise of thoughts, through the hustle of the day, through everything that distracts us from the main thing, you might hear it, a faint whisper from the abyss, the voice of humanity going into infinity. We are still talking to the cosmos, and the cosmos, perhaps, is listening. Good night.